morning, ladies and gentlemen. This is my presentation, Risks of Nuclear Aging. I want to speak about the technical characteristics of aging processes and their impacts on nuclear safety. First, I want to give some definitions. What's the definition of design lifetime? The IAEA defines it as the period of time during which a facility or component is expected to perform according to the technical specifications to which it was produced. And in this context, we have to see the planned lifetime extension. That means operation when the original design lifetime is exceeded. It means operation near or above the design limits. And it gets more and more necessary to have planned life management programs, and they are really essential, and objectives of them are to identify aging degradation mechanisms that can lead to an unexpected or unplanned functional failure. And IAEA itself says some countries already have advanced planned life management programs, where others still have none. First, I want to give an overview about the age of European NPPs in the European Union, Switzerland and Ukraine. Those countries took part in the European stress test. The average age is 29 years, and as you can see, next year more than half of the NPPs are older than 40 years, and some are older than 40 years. And Betzner 1 from Switzerland is the oldest one, with nearly 45 years. Here I have listed the country-specific design lifetime and lifetime extension in this table. And there you can see that the original design lifetime lays between 30 and 40 years, and most of the European countries have currently planned lifetime up to 60 years. The next slide shows the country-specific age structure, and there you can see that some countries had to phase out nuclear energy when they would shut down their NPPs after they have exceeded design lifetime. For example, Netherlands, but also Switzerland, who has 3 NPPs above 40 years, and the other 2 are also older than 30 years. And you can also see that in France and in Russia, more than half of the NPPs are older than 30 years. And what are the problems of planned life extension? One problem is physical aging, and it's most severe, the physical aging of the reactor pressure vessel, because the RPV, its vessel head and its internals have to withstand operational impacts, as there are gold-borne radiation that causes increasing embrittlement, material fatigue due to mechanical and thermal stresses from operating conditions, including changing loads, fast reactor shutdowns, and other events. throughout the operational lifetime. And also we have corrosion mechanisms which are caused by adverse conditions such as chemical impacts and mechanical stress or strain. Especially we have stress corrosion cracking, which is caused by tensile stress and aggressive chemical environment, and also irradiation. This is remarkable because the replacement of the RPV is nearly impossible for economic and practical reasons, also like the replacement of the containment. And in this context, we have the first case study concerning the RPV aging in Dole 3 and Tihange. In June 2012, undeclared defects were detected in the whole cylindrical part of the RPV in Dole 3, and in September also in Tihange 2. And in Dole 3, nearly 9,000 flaws were identified. Both reactors were disconnected from the grid, and a number of investigations were started in several countries of Europe. And the origin of the flaws was identified as manufacturing defect from the beginning on, which increased. And in May 2013, the Belgian Federal Agency for Nuclear Control stated, however, there is little literature or experience about the influence of irradiation on flaw propagation and zones with hydrogen flames. Hence, the potential evolution of the flaws under irradiation cannot be completely ruled out at this stage. And in the same month, the German Reactor Safety Commission, which is the highest board for reactor safety in Germany, stated that comparable RPVs in Germany were sent back to the manufacturer and they have never entered operation in Germany. Nevertheless, the Belgian authorities permitted continued operation of Dole 3 and Tihange 2 in spite of reduced safety margins concerning the integrity of the RPVs and uncertainties as to the further development of the flaws. Both reactors were reconnected to the grid in June 2013. And both reactors are nearly 30 years of age, and they have been upgraded. Another case study concerning physical aging of reactor pressure vessels internals. Here is shown the picture of a boiling water reactor, a cross-section, and the outside you can see the cross-section through the reactor pressure vessel, and inside you see the core shroud which consists of several rings which are welded, and in the early 1990s there were there were detected cracks at the core shroud welds, at the circumferential core shroud welds, and the problem is that these welds, these cracks are growing in their number and also growing in the length. And the critical crack length, which should be the criterion for obligatory replacement, was recalculated twice before the cracks had exceeded the initially calculated critical value. And this demonstrates how the original safety margins have been gradually decreased and moved on. And why is the function of the core shroud so important? The safety functions are to support the nuclear core under all loading conditions, maintaining overcoolable geometry, assure control, rod inversion and reactivity control with this rather serious, direct and ensure emergency cooling flows, assure availability of monitoring instruments, and allow recovery to safe shutdown conditions. So an aging mechanism at such components is very serious. But we don't have only physical aging, we also have conceptual and technological aging. The specific basic design, the site-specific basic design of older plants has a weak protection against earthquake and flooding usually, not in all cases, but rather often. And this is also seen in Fukushima. But also another example for conceptual aging could be seen at the Fort Cologne nuclear power plant in the United States. We had a flooding only a few months after Fukushima, and this demonstrates the conceptual aging of the plant, and it demonstrates also that comprehensive backfitting measures are not always conductible, and sometimes they are impossible. Now I have another example for physical and conceptual aging of electrical components. The operators often say these components belong to the conventional part of the power plant and are not safety essential, but here you can see an example about the unit transformers. The unit transformers are the interface between the nuclear power plant and the transmission grid, and they are often as old as the reactor itself. And due to economical reasons, comprehensive test procedures are conducted on aging transformers instead of replacement. Nevertheless, aging unit transformers and their protection systems often give rise to incidents resulting in reactor scrambles and even compromising mechanical components of the NPPs. And the last is also serious. As could be seen at the Swedish reactor Force Mark I in July 2006, when a two-phase short circuit in the transmission network caused a voltage drop at the unit transformer and a disconnection from the network. And now comes the problem. Further propagating failures of electrical components caused a severe incident which nearly resulted in a complete station blackout of the power plant. Only 2 emergency diesels started. Due to the outdated electrical design, the external transient was able to propagate in the safety-related components of the reactor. And after this incident had happened, a lot of investigations started in Europe, but nevertheless, and also in Sweden, but nevertheless, on May 2013, another serious incident affected Forsmark 3 due to failures of electrical protection equipment. And to see how often this beginning of such an incident happens, I have listed reportable events from with generator transformers in Germany in the last years, and you can see 6 events, and in 5 events later the generator transformer had to be exchanged. Yes, what means aging? Aging means decreasing of safety margins, the gap between safety requirements according to the state of the scientific and technological knowledge gets larger, and it gets also larger with refitting. And not enough that we have physical aging at the older NPPs, we also have often power uprating. What means power uprating? It means a process of increasing the maximum power level at which a commercial reactor may operate. To increase the power output, the reactor will be refueled with either slightly more enriched uranium fuel or a higher percentage of new fuel. The power upgrade forces the reactor to produce more thermal energy, which results in an increased production of the steam that is used for electricity generation. A high power level thus produces a greater flow of steam and cooling water through the systems and components. And all the components must therefore be capable of accommodating this higher flow. Moreover, also electrical transformers and generators must be able to cope with power upgrading.
Simone, we will speed up, please.
Yes, okay. The components must be able to fulfill the more demanding conditions that exist at the higher power level. It means higher stress to the reactor and additionally reduces the safety margins. And now I have a picture which shows which countries have large power uprating. For example, Finland with more than 33% at Okoinstitut. And together with Louisiana, we have 600 megawatts operated, which replaces an NPP. But also in Spain, Sweden, and Belgium, we have high upgrades of older NPPs. And it has to be seen that in France, the upgrades are only in 4 NPPs which are older than 30 years, but they have 27 older than 7 years. And it has to add it that the NPPs in the United Kingdom don't reach 100% of their design capacity. They have to operate with 70 to 80%. Due to severe aging mechanisms at their intervals. So what are the general conclusions of my presentation? Physical aging of components in nuclear power plants leads to degradation of material properties. An increasing level of material degradation is lowering the original safety margins. The site-specific design basis of older nuclear power plants was usually rather weak concerning external hazards. Comprehensive retrofitting is difficult to implement in older power plants. And power uprating imposes significant additional stresses on nuclear power plant components. Aging mechanisms can be exacerbated by these additional stresses. Reactor lifetime extension and power uprating are leading to a progressive decrease in the safety level of the older reactors in Europe. That can particularly become a problem in the case of incidents when the reactor is subject to more severe conditions than during normal operation. And this is very important. Aging can initiate incidents and worsen the course of accidents.